We spent the day yesterday talking about the speed of light. Now, going into yesterday, we knew the speed of light was 3 times 10 to the 8 meters per second for any kind of electromagnetic radiation in a vacuum, or in air for that matter. But how did we find that out? Well, there's been lots of experiments performed through history in the last several hundred years that have been used to determine, to one degree of accuracy or another, the speed of light. We started off with an experiment yesterday performed by Galileo a few hundred years ago, which pretty rudimentary, pretty simple experiment. Okay, good idea, didn't work so well though. Started off with two hills, about a kilometer apart. Okay, hill number one, hill number two. Guy standing on hill number one with a lantern covered up. Guy standing on hill number two with another lantern covered up. Guy number one starts his stopwatch, uncovers his lantern. The light goes toward guy number two. When guy number two sees that light, he uncovers his lantern. His light travels back to guy number one, stops the stopwatch, knows how much time that it took, knows the distance that it traveled, 2 kilometers-ish. Divide that by the time, measure the speed of light, right? Good idea. Problem is what? Yep. The reaction time is way bigger than the time that it would take the light to go from hill 1 to 2 and then back again. The reaction time would be in the order of half a second maybe. The time that it took the light to travel that far would be 10 to the minus whatever seconds. The reaction time is way bigger than the actual time itself. So even if we happen to get a number that was, I don't know, maybe 2 times 10 to the 8 meters per second, hey, that's not a bad value. But it doesn't mean anything. Okay, odds are we're not going to get a number that's close to the currently accepted value, but even if we do, okay, it's a purely random number. Okay, it's purely by luck that you would have gotten a number that was close. So it doesn't mean anything. Then we zoom forward to Nicholson, who performed a better experiment to determine the speed of light. In fact, he performed more than one type of experiment. We talk about this one, the rotating mirror experiment. Okay, this mirror has 8 sides to it. If you're looking at it from above, there's a face of the mirror here, and a face of the mirror here, and so on and so on and so on. Okay, those faces will all reflect light if struck by light in one direction or another. Now, let's say that we do have a beam of light, a flash of light. This mirror, by the way, is going to be rotating like this. We'll say it's rotating clockwise. We'll get a flash of light that reflects off of side 1. That flash of light is going to reflect off of side 1 down here to another hill and another mirror that's about 35 kilometers away. Now, we could do this experiment where it was 30 kilometers away or 40 kilometers away, but Nicholson's experiment, it was 35 kilometers away. So it reflects off of side 1, goes down to this hill, 35-ish kilometers away, and then reflects back. If this mirror isn't moving, hey, it's all good. If this mirror isn't moving, then the light's going to reflect off of side 3, just like this. It's going to get detected by, Mark, you ready for this? It's going to get detected by an observer with an eye that happens to be standing there waiting for it. It's all good, but we haven't determined the speed of light yet. Now we got to start rotating the mirror, start spinning the mirror on its axis. Let's say we've got this flash of light that's reflecting off of side 1. It comes down here and it strikes this second mirror over here on this hill, Mount San Antonio, 35 kilometers away. But in the meantime, this rotating mirror has moved. Right, Mason? This rotating mirror has moved. So now side 1 isn't where it was. Side 3, the side of the mirror that was reflecting the reflected ray, is going to be like something like this. Now this ray of light that comes back here maybe reflects off of it and goes up here. Never gets detected by the observer. That's not going to work. We want it to be detected by the observer. So we got to make the mirror spin a little bit faster. Instead of reflecting off of the mirror when the face of the mirror, the third face of the mirror, is in the position that it's currently in, we make this mirror spin a little bit faster. Maybe the face of the mirror, face 3, is in this position. So now this ray of light comes back here, reflects reflects back here. Oh, going in the wrong place still. Maybe we got to make it go a little bit slower. Maybe we got to do it something like this. Maybe we got to make it go a little bit faster so that, here we are, so that this ray of light reflects off of not side 3 at the wrong angle, but that it reflects off of side 2 at the correct angle. When the mirror was stationary, it reflected off of side 3 and got observed by the observer. When we started spinning it, it reflected at some kind of crazy direction and never got observed. But we spun it faster. Side 2 came in to replace side 3 during the time that it took the light to go from here back to here. And if it did that, if it made exactly 1/8 of a rotation, right? Side 2 was where side 1 was. Side 3 was where side 2 was. If it's made exactly 1/8 of revolution, then the angle is right, such that that ray of light will reflect and get observed by the observer. So, if we turn up the frequency of this spinning mirror, we turn it up, we turn it up, we turn it up, we turn it up until this guy observes something, then we know the mirror has made exactly 1/8 of a rotation during the time that it took the light to go from here back to here. Does that make some sense? Now, that's good news because we know the frequency of the rotation of the mirror. It's going to be somewhere in the range of probably 500-600 hertz, 10 to the 2, most likely at least, 10 to the 2 hertz. Okay, that's a measurable number. And it's not dependent upon reaction time. It's a measurable number. From the frequency, we can get the period, the time for one complete rotation of this mirror. That's not what we want, the time for one complete rotation, because it's only made 1/8 of a rotation. So from that, we can get the time for 1/8 of a rotation. Now, knowing the distance that the light traveled, in this case it would be 70 kilometers, knowing the time that it took for 1/8 of a rotation, which is exactly the amount that the mirror must have rotated in order to be observed by the observer over here. Knowing those two values, then we can measure or calculate the speed of light, which we're going to get, we don't know exactly. Okay? It's not necessarily going to be exactly 3 times 10 to the 8, but it's going to be something reasonably close to the currently accepted value of 3 times 10 to the 8. Why is this so much better? Well, we're dealing with a distance that's 35 times the distance that Galileo dealt with. But you know what, honestly, that's not a huge factor at all, because the light still travels from one hill to the other and back again in a ridiculously short period of time. Way, way, way too short for reaction time. Okay, reaction time would still be way too big to ever make that a viable method, even if we did increase the distance between Galileo's hills to 35 kilometers. What makes this a better method? What does it take away from the equation? Yep. Human error takes away reaction time. Okay, we don't have any reaction time here. It's a mechanical device that's predictable and does the same thing every time that we can calculate other things from, as opposed to measure other things from. All right? Now, when it comes down to it, hey, everything you need to know is up here. But in practice, solve these problems, it's going to boil down to this, Parker, right? 2 equations. V is equal to d over t, okay, my constant speed equation, because light travels at a constant speed. And then t is equal to 1 over f. Now, this is the time for 1/8 of a rotation. This is the time for one complete rotation. You're going to plug in numbers, and you're going to solve for something. I'm going to tell you right now, you're going to either solve for this or this. Okay? Doesn't matter. You're not trying to solve for one or the other. You're just solving for whatever happens to come out of the equation, whatever you got enough givens for. When you solve for this or this, good news is it's pretty easy to solve for. The bad news is it's not what you're looking for. Okay? Whatever time you get is always the one you're not trying to find, the one you're not looking for. If you get little t, you're going to want big T. If you get big T first, you're going to want little t out of it. Now, if I get little t and I want big T, how am I going to get it? Time for 1/8 of a rotation. Time for one rotation. Parker? Good. Times it by 8. If it's an 8-sided mirror. You saw problems yesterday where you had a 12-sided mirror, right? In that case, it would be multiply it by 12. What about this one? You got big T, you want little t. because it's one of those grass is always greener on the other side of the fence things. We're never happy with what we have, right? We get big T, we're not happy with that. We want little t. How do you get it? Yeah. Yeah. Divide by 8 or good, or you can multiply by 1/8. If you're more comfortable with multiplying in both cases, then it's multiply by 8, multiply by 1/8. Or if you like using the number 8 in both cases, then it's multiply or divide. Okay, whatever works for you. I'll always say this, divide by 8, but it's the same thing. All right, let's take a look at those 3 questions we had for homework last night on page 650. Any issues with any of these 3 questions? Number 2, okay. Number 2 it is. Light, doesn't say what kind of light, does it? What do they probably mean here? What kind of EMR do they likely mean here? Yeah, it's almost certainly going to be visible light, right? It's pretty hard to perform this experiment when you're dealing with light that you can't see. Okay, but it could be light that you can't see. You're going to get the same results if you had some way of detecting that light. Almost certainly going to be visible light, though. 8-sided mirror. Hey, my distance is quite a bit different this time. AM in kilometers. Usually my distance is about 35 kilometers. Whenever I'm solving a problem, a typical Nicholson problem, where the distance is somewhere around 35 kilometers and my mirror is somewhere around 8 sides, then there's a couple of things that we can remember. You don't have to memorize these numbers because, we know there's a lot to remember. But if they happen to be in the back of your mind, it can be useful for you in determining whether you're in the right ballpark or not. Usually, you're going to get little t to be somewhere in the range of 10 to the minus 4 seconds, and you're going to get frequency to be somewhere in the range of 10 to the 2 hertz. Now, in this question, we're dealing with a distance that's quite a ways off of 35 kilometers. I don't think I'm going to be that far off of those numbers that I predict here, but I might be off. Because it's, say, the number that I have in my data is quite a bit off of Nicholson's original experiment. Okay, let's crunch the numbers and see what we get here. We know that we've got to start with this equation and this equation. 1/8 of a rotation, the time for 1 rotation. Now, we don't know the speed here, or do we? We have to assume a certain speed in this question. What number are we going to assume, Kevin? Good. I know what you mean, yeah. 3 times 10 to the 8 meters per second. Be careful you don't make a silly mistake and put 10 to the minus 8, but I know you know that it's positive. Just check your data sheet if you get confused on that. D is, what are we going to use? 30 kilometers or 30,000 meters. Okay, it travels 15 kilometers there and back. We could solve, right away we can solve for T1/8. It's not the one we want, but it's some. 30,000 meters divided by 3 times 10 to the 8, I'm going to say is 1 times 10 to the minus 4. Is it? Now, we didn't know for sure that we were going to get 10 to the minus 4 here because our distance was so far off. But we did. Barely, but we did. What are we going to do with that? Kirsten, what are we going to do with that? Yeah, we're going to times it by 8 to get the time for 1 revolution. Or rotation, I should say. That's going to be, look, I'm having trouble multiplying 1 times 8. I think that's going to be 8 times 10 to the minus 4. In a lightning fast calculation by a brilliant mind, 1 times 8 is 8. Take this number up here. Frequency is 1 over 8 times 10 to the minus 4. And when you do that, 1 over an 8 is 1.25 times 10 to the 10 to the 3. Hey, we were kind of expecting 10 to the 2. Why did we not get 10 to the 2? It's almost 10 to the 2, right? 1,250, it's close to like 900, 10 to the 2. Why did we not get 10 to the 2? Numbers that we usually get for frequency. Look at our distance. What's the distance usually in these? Standard distance is about 35 kilometers, right? So we're off that by a factor of more than 2. Okay. You get a number for frequency that's 78 million. You're wrong. Okay, you're wrong. you get 10 to the 3, you might be right. Okay, in this case we are. Okay, doesn't raise a red flag because our distance was so far off of that standard 35 kilometer distance. Quinn, is that okay? Any others here, guys? Okay, we know our homework for tomorrow is worksheet number 14. Okay, so I think there was only 3 questions on that, right? See what you can do with that. We'll check that over tomorrow. Now, while we're on the topic of the speed of light, not so much how we determine the speed of light, but rather how we use the speed of light, I want to do just one example problem that really you could have done in Physics 20, but we're going to just refresh your memory with it here. Not a Nicholson experiment problem. Don't try to apply that. Okay? Just because you've been doing that for a day and a half now and you've solved a number of problems with Nicholson experiment, don't start doing the same thing. Okay? Look for the rotating mirrors. If you don't see it, don't do that. It's a good recipe, but it's only a good recipe for a rotating mirror experiment. This question, we have a distance between Calgary and Regina. It's about 800 kilometers. How long does it take the light to travel from Calgary to Regina? The wavelength of the light is 600 nanometers. What's its frequency? Well, we know the distance here is 800 kilometers, which is 800,000 meters, or we could just say 800 times 10 to the 3 meters. We want to know the time. We know the wavelength is 600 nanometers, or 600 times 10 to the minus 9 meters. You could have said 6 times 10 to the minus 7 meters. Either of those are fine, same thing. What's the frequency? Well, there's 2 things we want to find, so we're going to have to do 2 different things. Let's start off with V equals d over t, because light travels at a constant speed. It's not the time for 1/8 of a rotation. It's just time that it takes light to go from Calgary to Regina. Distance is 800 times 10 to the 3 meters. The speed is 3 times 10 to the 8 meters per second. 8 divided by 3 is 2.67 times 10 to the negative 3. Thank you. 2.67 times 10 to the negative 3 seconds. So pretty quick, right? Pretty quick. We said that light would make about 30 return trips across Canada in 1 second. So you got to figure it's going to go from Calgary to Regina pretty quick. Got the time that it takes. Pretty quick time. 2.67 times 10 to the minus 3 seconds. What about the frequency? Yeah, the wave equation, right? F is equal to V over lambda. Again, sometimes you're going to see that written as C is equal to F lambda, or even C is equal to D over T. It doesn't matter how you write it, as long as you know that V, or C, is 3 times 10 to the 8 meters per second. The wavelength here is, what, 600 times 10 to the minus 9. Gives me 5 times 10 to the 14 hertz. Hey, we were not asked this question, but what kind of EMR is this? What kind of light is this? Visible light, ultraviolet, X-rays? It's visible light, right? Because visible light is anywhere between 4 and 7.5 times 10 to the 14. We good there? All right. So worksheet number 14 is due tomorrow. You'll have a chance probably to work on that for a few minutes a little bit later on in class. I'm going to also assign worksheet number 15 as well. That's on this stuff. Okay, sounds like a lot, but honestly, both of those worksheets will go fairly quickly for you. So combined with the amount of time you're going to have in class here, that's not going to be that much work for you tonight. Good news is what we're about to do here now won't be any more homework with this. Okay, this is it. Okay, this is all your homework for tonight.